Precalculus. In this video we're going to be taking a look at set builder notation. Our I can statement for this video is that I can write set builder notation to describe the domain or range of a function. That's really why we bother learning about set builder notation, is it's a very technical way of describing a set of numbers that in our case is going to be describing some feature of a function. Our outline for this video is we're going to take a look at how to read set builder notation, and then we'll take a look at how to write set builder notation, looking at some different scenarios where we have a continuous set of numbers, where we have a discrete list of numbers, and then one additional wrinkle to this is using an additional variable inside set builder notation to describe a pattern of numbers. So let's take a look. Here is a set of numbers in this fancy set builder notation. The squiggle brackets are required. That's part of this. That vertical line right after the X, that's part of it. So let's take a look at how to read this by looking at the different parts of this notation. So the squiggle brackets and the X kind of go together, and we should read that as the set of all X. Now, if we had a different letter there, obviously we would say the set of all, and then whatever that other variable is that we're using. But in this case, we've got the set of all X, and then that vertical line in there is just simply read such that. And it tells us, what's going to follow is our pattern for this set of numbers. And then, well, that should all be black, but it should be read, -4 is less than X is less than or equal to 6. So altogether, that's read the set of X such that X is greater than -2. So it's a new set. We're using the same variable X. We've got a different rule in there, but we've got the same structure to our set builder notation. Now, whenever we don't have anything else noted, it's always implied that X is in the real number set, which is what we're usually working in anyway. We can change that if we want to. So here we have the exact same set builder notation, the set of X such that X is greater than -2, but we've put a limit on what X is. X isn't just a member of the real number set. X here is limited to being an element or a member of the integer number set. That weird looking Z thing with the double bar is our symbol for the integer numbers. Now with X limited like this, we're really limited to just the integers, -1, 0, 1, 2, 3. Not -2 itself, because it says X is greater than. Now let's take a look at a discrete list. Now notice the set of X such that X, that's all the same. This is just a list of numbers. This would be show up in like a table. So it's just a list of numbers that are exactly 0, 0.5, 1, 2, 5, 16. So this is a great way to just list a short list of numbers. Just write them all down. There doesn't seem to be any pattern to the numbers, so we're not going to try to do anything funny in this case. We're just listing the numbers that are the set. Now, if there is a pattern, and if it is an infinite list, we're going to have to do something different. But when it's just a nice short little list, something that I can write every single number, just write them all down. Now, if it is an infinite list of numbers, and there is a pattern to it, then we need to really do some digging in there and figuring out how to write this down. So this is a little bit of a wrinkle to this. You see another letter in there. You see N in there. So this is read the set of X such that X equals 2 times N, or 2N, such that, so another vertical bar, so another such that N is an element of the natural number set. So now we're using N to create an infinite number of numbers in a list. Now the natural numbers are the numbers like 1, 2, 3, 4, the positive integers. You can think of those as the counting numbers. So what this does is if I make a list for what N can be 1, 2, 3, 4, so on and so forth, I plug that in, 2 times 1 creates 2. So x can equal 2, 4, 6, or 8, and it continues on forever. So this is not a finite discrete list of discrete numbers. This is an infinite list of discrete numbers. It goes on forever. So what if I have an infinite list? We see that dot, 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 5, 20, 45, 80. There seems to be a pattern here. I know that at least these are all multiples of 5. So if I'm trying to figure out my set builder notation, I think I'll go ahead and divide by that 5 and see what I get. So 5 divided by 5 is 1, 20 divided by 5 is 4, 45 divided by 5 is 9, and so on. Oh, this is a list of the perfect squares, 1, 4, 9, 16, blah, blah, blah. So I will use the perfect squares to create my set builder notation. So the set of all x such that x equals 5 times n squared. Now again, I only want to use the natural numbers. I only want to use the counting numbers. I don't want to plug in 1 and negative 1. I don't want to plug in negative 2 and 2. So I don't want to plug in all the integers. I just want to use the natural numbers, the counting numbers, 1, 2, 3, 4, so on. So here's my set builder notation for that discrete list of infinite numbers, 5, 20, 45, 80, and so on. Okay, so here's our I can statement. I want to revisit that. Can you write set builder notation to describe the domain or range of a function? All I'm really worried about, can you write set builder notation? If you're looking at this and you're going, well, I can do that, but I don't know what the domain and range of a function is, we'll talk about that later. So that's it. I'll see you in class, and I'll see you online.